going to be looking at the 2017 questions. We're going to kind of run through the first three of those questions in this video. The first question is really about linear regression, really just about the basics of line of best fit and residuals. The first thing it looks at is it gives you a description of X, which is in meters, the length of the wolf from tip to tail, and the weight of the wolf in kilograms. And asks us, and it tells us that it's a positive, linear, and strong relationship between those variables. What does that mean for these values? One, for positive, now you could have had something slightly different than me, but basically it means that the both variables are going to be increasing at the same time. So the longer the wolf is, the more the wolf is going to weigh. I try to write that in context. They definitely want you putting all this stuff in context. And you wanted to say for each variable, as one increases, the other also increases. That's what a positive residual would mean. For part 2, linear, this is essentially saying as we add an additional X, so that would be additional meter in length, then we know the weight is going to increase in exactly the same amount, well, not exactly, but approximately the same amount each time. So maybe we should add a little bit to that and say, whoa, too thick. Zoom in a little bit. On average, I don't want to give it, it's going to be the exact same amount every single moment, because that's not in fact true. It's just an estimated amount. So make sure that when you write this out, you're putting on average, or this is an approximation of what's going to happen. When you're looking at strong, I mentioned that when we go to predict for a value, that our prediction is going to be close to the actuals. So I was saying it has a small residual value, or that my predictions, my observed, are going to be close together. You could have said this in a lot of different ways. As long as you were saying something that lines, that the dots, the points are going to be really close to my line of best fit, then you essentially got this part right. For the next part, for part B, it asks us to interpret the slope of the least squares regression line. And we say for each additional meter in length, we would expect the height of the wolf to increase by 5.302 kilograms on average. Pretty straightforward there. In part C, it was asking us to find what the actual observed weight is. So we needed to find its predicted value and use our residual formula. So I basically plugged in the value they gave us into my line of best fit. I found the predicted weight, and then I plugged in residual and the prediction and solved this for my observed weight. And that's number 1. Number 2, this is a confidence interval question. This is actually pretty straightforward, at least for part A it is. Number 2, they give us a random sample of 80 customers where 23 of those customers had ordered water, and instead of getting water, they ended up getting a soft drink from the beverage fountain. They wanted us to construct a 95% confidence interval for the proportion. I went ahead and made sure to note that was categorical, and determine that confidence interval. So things I needed to do, this is definitely independent. They also wanted me to check success or failure. I didn't need to check the other 2, but I went ahead and did it anyways. I needed to justify that there were at least 10 successes and 10 failures so that we could assume that the sample was large enough to consume, or that it was considered it normal. We were using a 1 proportion z interval. With the calculator, I got this interval to be 0.18832 to 0.38668. And I'm 95% confident that the proportion of customers who ask for water but fill the cup up with soft drink is between 18.8% and 37.8% on average. In the next portion, so that was just for part A, and for part B, I guess that starts up about right there. For part B, it said, well, suppose that it costs the restaurant about 25 cents per person that does this. If they had 3,000 customers in the month of June, then we wanted to estimate how many how much was the restaurant losing when people tended to do this. And so that we knew that this percentage of customers are going to do it. So we needed to know a lower and an upper bound in terms of the number of customers. So that's the first thing I found. I multiplied my endpoints by 3,000 to say, well, we would have approximately 564.96 or 565 to 1160 or 0.04. I left them as decimals until I got to the end because I knew it was going to be decimals with money. So this gave me a boundary that I was expecting this few of people or this large number of people to be able to do this out of the group of 3,000. And so I did that, and then I multiplied the number of people times the 0.25 because it cost them 25 cents per person. And that gave me a lower bound of 141.24 or 24 cents to $290.01. And so I said I predict the restaurant would lose between, or I'm 95% sure that the restaurant would lose between $141.24 to $290.01 per this particular month. There are months like this, which is in June, on customers who fill their cups with straw drinks when ordering water. I use the word predict here to estimate this is my response, not that it's an exact response. You could have said the words on average at the end down here, or you could have said they would lose approximately this much money. Any way you did it, you wanted to make sure that it wasn't a deterministic language where you said it's exactly this amount of money. You wanted to give it that it's an approximation. And that's question 2. Question 3, this is a probability question. To be honest with you, this felt a lot like some of the questions that we had in class. Pretty straightforward, actually. In part A, it's asking us something real simple. It's saying, for a melon from distributor J, then, here we go. For a melon, for a single melon, what's the chance that it's going to have a diameter greater than 137 millimeters? Because they told us that it was approximately normal, and we had the mean and the standard deviation, we could go straight to drawing a picture like this, or if you're not drawing anything, you could just simply define it, a normal distribution with a mean of 133 and a standard deviation of 5, and we wanted to find the area under the curve greater than 137. Right, and so I did that here, and I wrote that out, and it's 0.21186. You had to have, if you just did this part, you had to define each one of these numbers. If you had this, then that sufficed to define each of your values. For part B, it gives us a new distributor K, and it asks, well, if it's 84% likely that they have a diameter greater than 137, and that 70% of the distributor of the melons come from J and 30% from K, given all that information, we wanted to know what's the probability that if you walked into the grocery store at random, then what's the chance that you'll have a diameter greater than 137 millimeters? This reminded me a lot of some of the probability questions that we did. And so I thought, this would be a great chance to use my tree diagrams because I have 2 events, and both of those events only have 2 outcomes, right? So the melons either came from J or they came from K. And so I could figure out those probabilities really easily. They told us that, actually. And then from J, well, either the melon was large enough to be considered greater than 137 or it wasn't. And so since we had this probability from part A, I could subtract this from 1 and get the probability that it would be less than 137, right? And I could do the same thing for K. And they told us that the ones that are greater than 137 millimeters was a probability of 0.8413. So you could subtract that from 1 to get the other side of that. Now, I didn't need all of these. Technically, I only needed this and this, so getting these extra pieces here are not even required. It's not even necessary to do that. I just was in the habit of doing it, and so I kind of filled it all out. So I needed to know that the probability of getting a melon greater than 137 millimeters was the fact that it could have come from store A, but it could have come from distributor J, or it could have come from distributor K. Since it's an OR question, I know that was an addition rule problem. So I basically found individual probabilities by multiplying them together and getting the sum of those 2 results. So about 40% have a diameter greater than 137. Part C says, given that it came from a grocery store and it has a diameter greater than 137, what is the probability that it came from J? So this is definitely just like some of the things we've done. So I wrote the actual formula down, and I needed to write the formula out or somehow write out how I calculated this probability. If you just put the probability in, then you would have only gotten partial credit at best. But if you wrote down the conditional formula and the fractions, then you would have gotten full credit for this part. So I knew that I had they're both of them, the and part, because that's what we did up top in this part here. And so I'll put that probability here. And I know that just having a diameter of 137 or greater is exactly what we did in the last example here. And so this is very similar to the forbidden material question, if you remember that, from chapter 15. And so I put that new probability down at the bottom. And then we simply divided, and it gave us that about 37% came from distributor J. And this concludes the first 3 questions from the 2017 exam. If you got questions, rewatch it or send me an email.